Redshift. If you asked a 3-year-old to do an impression of an ambulance or a police car, firstly, your eardrums might suffer and it might just be a really annoying situation, but more importantly, their impression will most likely include the effects of Doppler Shift, and believe it or not, this annoying toddler is actually giving us an insight into the very nature of the universe. The Doppler Shift is the effect that moving can have on the frequency of waves. If we think about an ambulance that's stationary relative to you, the noise will be constant and all sound the same no matter where you are standing in relation to the ambulance. But if the ambulance drives past you, the pitch of the sound will change. As the ambulance moves towards you, the pitch increases, and as it moves away from you, it decreases and the siren sounds lower. That's how we get our nee-nor, 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 nee-nor effect. Let's think of that ambulance moving towards us. It releases a sound wave, and by the time it releases that second wave, it has moved forwards. In effect, you can think about this as it kind of catching up slightly with the sound wave it had released a fraction earlier. This means the sound waves out front will be closer together. Closer together waves means a higher frequency, and we register this as a higher note. For the waves behind the ambulance, you can think of the ambulance as kind of running away before each subsequent wave. This means that the waves will become more spread out, and therefore have a lower frequency. We register this as a lower note. It's this concept of chasing the previous wave, leading to a higher frequency, and moving away from the previous wave, leading to a lower frequency, that is important to explain redshift. Now, one feature of the Doppler effect is that it actually works for any type of wave. Now, we tend to think of its association with sound because sound is slow enough for us to hear the effect in our everyday lives, and because our ears can easily register a frequency difference on these scales. However, because any wave that does this Doppler effect, it also occurs for light. If I therefore replace the ambulance with my face, which is of course a shining beacon of light, we'll use a torch, we can think of the Doppler shift of light. If the torch is stationary and not moving, it doesn't matter from which direction I actually look at the torch, it will be the same colour light, just like the same pitch for sound. However, if the torch is moving towards us, the torch catches up slightly with the previous light wave emitted, so the light bunches up, and we have a higher frequency, exactly the same for sound, but this time for light. A higher frequency for light means that the light will appear slightly bluer. Now that doesn't mean that the object is actually blue, it just means that the object appears bluer than it would otherwise when we compare it to when it was still. It has a bluish tint just from moving towards us. If the torch is moving away, then again we can think of it running away from each previous wave. This means that the light is more spread out and it has a lower frequency. Now this means that the light will appear redder than it would do normally. A reddish tint has arisen from the torch moving away from us. Now, if we look at distant galaxies, they are moving fast enough relative for us to see this effect. If we look at the light coming from the galaxies, we can match it up to data we can measure on Earth, which tells us what the light should look like if it wasn't moving at all. Therefore, we can tell, by doing this comparison, if the light is redder or bluer than it should be. And therefore, we can tell if that galaxy is moving away or towards us. Now, when we look at this and the galaxies around us, we might expect them to appear bluer. This suggests, remember, that they are moving towards us. And we expect this is because of gravity, which likes to pull things together. However, we don't see this at all. Actually, it's the exact opposite. When we look at the light from distant galaxies, they almost exclusively appear redder. This means that almost all galaxies are actually moving away from us. Because remember, lower frequency light, moving away, gives us this red tint. If we rewind this idea and backtrack, it means that because we're all moving away from each other now, we were once all at a single point, which annoys people in support of Brexit, I'm sure. This expansion from a single point is what we now call the Big Bang. We know of its existence just by looking at the shift in light from distant galaxies using an effect that even a 3-year-old can vocalise. That's pretty nifty. So one last thing. Remember that the faster the galaxy is moving, the bigger its shift in the direction it's going. Just think that if the galaxy is moving faster, it will chase or run away from the light more, and therefore have a bigger shift towards the blue or the red. In summary then, the Doppler effect also works for light, so objects moving towards us have a higher frequency light than they should, and we call this a blue shift. Objects moving away have a lower frequency than they should do, and we call this a red shift. If we look at the universe, almost everything is actually redshifted, which means it's moving away. If everything is moving away, it probably meant that we were all at a single point at one point, and the Big Bang expanded us out.
Questions.
When objects move away from us, how does this affect the frequency of light, and how does the object appear? When the object moves towards us, what happens to the frequency and appearance now? What does the evidence of this shifting light suggest about our universe?